Yeah, so the 2 points here. The first one is how it is evolving. So it's evolving pretty fast and in a very positive way. So this evolution is happening because of two or three major reasons. The first one is compared to about 5 or 6 years back, today the awareness about using genomics in healthcare has significantly increased for various reasons, which includes increased awareness among the healthcare providers, increased awareness among general public, increased awareness that is because of various scientific publications that are coming up, changing guidelines across the world. So because of all these reasons, the awareness has significantly increased. The second reason why this positive evolution is happening is the reduction in the costs of either a regular genomic test or sequencing of DNA. There's a significant drop in the cost across the globe. So this is becoming more affordable, relatively at least, compared to 5 6 years back in the country. So this has caught up large number of healthcare providers and patients. So it's a good evolution that's happening. The third important thing is there are roughly about 8,000 to 9,000 rare genetic disorders present across the world. People are affected by this. However, in the last decade or so, there has been significant achievements in identifying the root, exactly what is the genetic cause of these diseases. And even today, as we talk, every year 100 to 150 new genes are identified which cause these rare genetic diseases. So even though they call it as rare, for countries like several countries in Europe where there are smaller demographies, smaller populations, it can be considered as rare. But if you look at the demography, we are talking about 1.4 billion population, largest demography in the world. For us, even the so-called rare definition, today it's pretty common for us, and many clinicians every day in a tertiary setup see at least about 10 to 15 rare disease patients a day. So it's not any more rare. So only thing is, each disease entity, each rare disease is relatively uncommon compared to the common diseases like diabetes or cardiovascular disease. But all these 8,000, 9,000 put together, it's a large burden for the country like India. So it's very important that we democratize genetic testing, quality genetic testing, to at least identify what specific disease the patient has or individual has, or what kind of genetic variations they have which make them susceptible to certain diseases, and take up necessary measures wherever. It could be treatment, it could be prevention, it could be setting up the expectations of the patient, or it could be next generation, how do we prevent these diseases. So this is something that is increasingly accepted by across the population, including the regulatory and government agencies, which is a good thing. So if you ask me, among the top major impactful things that have happened in science and technology, which made this whole, not only just diagnostic testing in genomics, but whole of new drug therapies, new treatment options today are coming. We are talking about biology, biotechnology, biosimilars. Whole of this field is one aspect, is one impactful thing that has happened is the development of new generation of DNA sequencing technologies, which has happened last maybe 14, 15 years, but more so in the last 6 to 7 years. There's a dramatic change. Now, two things have happened. If you look at conventionally how 20, 25 years back DNA sequencing was done was by a conventional method called Sanger sequencing. Basically, it's named after a scientist, a Nobel laureate called Fred Sanger, who got a Nobel Prize for identifying the way it is sequenced. But the biggest limitation with that was it was not a scalable way of sequencing. So today, if I have to sequence the whole genome or even larger part of the human genome, or larger part of the human genome in 1,000 individuals in just about a 1 week's time, it was never possible by the conventional methods. And if you have to do it, it was super expensive. Just to give you an example, the Human Genome Project, the draft genome project, which was published almost about 20 years back, it costed them $1 billion. And they finally submitted one draft human genome sequence. So from then, the evolution of these technologies have happened so dramatically. Today, the sequencing technologies have defied what you call Moore's law. So Moore's law is a law that explains the semiconductor industry as how the capacity of the semiconductor industry is growing and how the prices are falling down on the chip. So the only other technology which has actually defied the Moore's law and has actually increased the capacity and decreased significantly the price is the DNA sequencing. So this is a major impactful event in science and technology that has happened. And as we talk, there are more and more methods which are cheaper, which might tomorrow can become in such a way that you can on the go, you can sequence your genomes at just few dollars, $10 to $20. Everyone has to believe one concept. Every disease is genetic in origin. Every trait is in genetic in origin. But how much is the genetic component varies from disease to disease, entity to entity. Today we classify broadly the diseases into two categories. One, we call it as monogenic diseases. Basically these are genetic diseases where the only cause of the disease is a changes in the genome that happens in an individual. And that's something that we do regularly. Everyone, it's a proven beyond concept, and we test them to identify what are the genetic changes that are there. But the second category of diseases which are more prevalent and what we call common diseases or complex diseases, and you can categorize them as non-communicable diseases also, which includes diabetes, coronary artery disease, Parkinson, Alzheimer's, schizophrenia, hypertension, stroke. So these are all diseases where there is an amount of genetic component definitely playing, and interplay of these genetic factors with lifestyle, environmental factors, and the outcome of the disease happens. Now, last several years, there has been no way as to how you quantify these genetic changes that predispose an individual for the common complex diseases like heart disease or diabetes. So last about 7 to 8 years, there is a concept called polygenic risk score. There are different versions of polygenic risk score. We call genome-wide polygenic risk score or just polygenic risk score. So basically, as it mentions, the meaning says polygenic. So there are many genetic factors that are taken into account. Risk score is a statistical score based on all the changes that are there in the genome or set of genes. This statistical method basically aggregates all the effects and quantifies into one risk score. So this is a risk score given to an individual after studying the variations present in that individual, and it's not a diagnostic test, it's more of a screening approach where an individual can be stratified whether he has got a high risk score or average risk score. If an individual has a high risk score in a well validated test, which means his genetic risk or his genetic susceptibility is pretty high, and he has to be more aware of other modifiable factors, which includes lifestyle, which includes environment, the food, or any interventional things that he needs to do, like taking drugs with the help of the clinician or physician. These are the things that he needs to take care to ensure the mitigate the total risk, which includes the genetics and lifestyle risk factors. So this concept on the implementation of the clinic or at the large in population is growing attention. The science is becoming mature. More and more scientific publication validations are being done across the world. There are technologies like deep learning or AI, machine learning are being basically implemented in the large data sets today. In the next several years to come, maybe 3 to 5 years to come, we will be doing this as a preventive approach for every individual to understand their risk for getting common diseases, and accordingly mitigating measures will be implemented. And this can be done at large, at a scale, at a population level to identify population level susceptibility to various diseases, and governments can implement certain programs where large scale non-communicable disease epidemics can need not happen. So today we are talking about 100 million diabetics in the country. So how do we do that? How do you reduce the burden? Apart from treatment, apart from other measures you take, if you can identify individuals at much early age, at the age of 30 or 35 years, based on their genetic predispositions, you can put up some large scale measures to reduce or mitigate the risk by interventions done at the population level. And certain pilot programs in these polygenic risk score are happening in UK, in National Health Services, to see whether these can be implemented at population scale. If they can implement it, what are the costs that are incurred by the government, and is it practically possible or not? So we'll be seeing in the next 1 to 2 years to really come up with some real time or real world data as to whether these polygenic risk scores will be really helpful in effective risk stratification and mitigating the disease burden of the world. One of the major problems in eradicating or significantly mitigating the problem of tuberculosis in the country is identifying multi-drug resistant cases, or even extreme drug resistant cases we call XDRs. And today there are even certain drugs which can be prescribed if you identify individuals who are MDR. And government has launched a certain good programs, Stop TB program. And if we need to achieve, we need to come up with multi-pronged approach, not just diagnosing individuals with tuberculosis, but also identifying individuals who have multi-drug and extreme drug resistance cases. How do you identify that? One of the easiest way to identify is when you get the sample from the individual, the suspected individual with tuberculosis. It could be a sputum sample, it could be a pulmonary sample from the lung, or even extrapulmonary samples. You basically look for the DNA of the tuberculosis in the sample, and if you can sequence it and understand what are the mutations present in the TB genome or tuberculosis pathogen genome which can make it resistant to the drug, it is the effective way of identifying an individual who can be put on special drugs and special regime and mitigate this complete disease. And as a part of it, about 4 years back, we developed a very simple but very effective sequencing based test where you don't need to culture the sample. Today, one of the challenge in tuberculosis testing is for many aspects, especially drug sensitivity, you need to culture the sputum sample and you grow the bacteria. And tuberculosis is a fastidious organism. It takes anywhere between 2 to 4 weeks to grow, and sometimes you will not be able to grow that also. So to completely eliminate this issue, we take sample directly from sputum or even cerebrospinal fluid. We just sequence the TB DNA in that sample within about 4 to 5 days time, and we can even go down to the cost of 4 to 5,000 rupees, and we can sequence the whole TB genome, 100% of the TB genome, and give a report within about half an hour's time as to which are the mutations present in that patient sample which are causing either MD or XDR. If you know, it's well and good. If you don't know, we can identify and give it. So this can identify across the country every tuberculosis individual, what are the new mutations, what are the novel mutations that are there in the pattern, like have you seen during COVID time, how COVID sequencing help identifying Delta strain or Alpha strain or Beta strain. The same way we can identify these mutations and help either surveillance teams from the government or healthcare providers to give proper drugs and monitor the patients so that this tuberculosis will not spread across the country. So this is our solution, and I hope government will take some initiatives to support us, at the same time adopt these technologies to augment the efforts of Stop TB program. Today we are in the world of what we call data biology. Even if you see in our companies also, the wet labs are shrinking, the dry labs are expanding, which means the data is becoming very important and data is very valuable, as long as it's a quality data and well quantified data. And genomic data is no exception. Today and in the next 7 to 8 years come, there will be several organizations, several entities which will keep sequencing more and more genomic data as a part of any other effort. So when you have so much of data, the positive sides of it is you can use this data in a responsible way for identifying and understanding the biology of the disease, to come up with novel treatments, to identifying new insights of the disease itself so that we can counter them much better. There are commercial interests, nothing wrong about it. There are scientific interests at large, So it is very important that this data is used in a very, very effective manner. And we have to use it, and especially with the new technologies on artificial intelligence, neural networks, machine learning, and many other deep learning methods that are coming up, these will become much simpler and much better. Having said that, the way how we generate the data, how we store the data, how we share the data, and how we protect the privacy of the data is paramount importance. And as we talk, you know that government has tabled the revised data privacy law in the parliament a couple of weeks back, and there's a lot of debates going on, and some clarity is coming through, and it's very important we come up with these privacy laws so that it's very clear for everyone, especially the industry, so that they can plan accordingly and ensure that everyone is compliant to the law in a proper way. Second is, globally, there are pretty robust laws. If you take Europe, there is what we call General Data Protection Rights or rules, GDPR from Europe, and there are similar laws in US which govern both the protection of genomic data, rights protection of the end consumer or a patient or individual, at the same time in a responsible way, using this data in a de-identified manner for various aspects of identifying new things, new treatments, new molecules, or just trying to understand the disease insights. It's happening. So we have to come up with our own laws. Some of them should be customized to a country like India. It may not be generalized for Europe or US, in a very business friendly way, at the same time protecting the rights and protecting the data privacy of the individuals, because this is all sensitive personal information. It should not be exploited. How we use in a balanced way decides how successful we are going to be using these large data sets, not just in genomics, but also in the healthcare data sets. As long as utilizing the old genomic technology, whether it is sequencing, whether it's analysis with the data or whatever it is, we are still at the scratching the surface of the applications of the whole paradigm of utility that it can give. Having said that, the more science that is coming up across the world, the more amount of information that's coming, more clinical utility, more translation side is coming, the whole pie of application is growing. So when the whole pie of application is growing, the whole pie of the geography, the market share, market potential is growing. So one shouldn't consider a competition as something, really a pain. We should consider competition in a very positive way. Competition augments innovation. And for a country like in India, we need a lot of innovation to happen. Competition reduces the price, brings affordability to the end consumer. Competition also gives you an advantage to push the limits and talk to various stakeholders, including government, as to how we can democratize this. So there are several aspects, and a country like India, where it's pretty free, it's not very restricted, competition is very good. We are putting up a roadmap as to how India can make genomic technologies or analysis methods for the world, not just for India. So there's a much larger market that we are looking for, and that's something that we aim to do.